Dear colleagues, my name is Artem Sukhov. Today I'm happy to present you our solution of problem that names Curie engine. And this is a device that consists of a nickel disc fixed on an axis by the bearing and nearby a magnet and burner. If you start the warm up the disc, then it starts rotating. And to begin with, it should be said that the entire effect is based on a second order phase transition. The temperature point of which is called the Curie point. And if we expand the free energy in assumption of a solid and neglecting parts of a small order, we can express the magnetization of our nickel in terms of the Curie point. And we found this temperature for nickel. An important result is that about this point, the metal loses its magnetic properties here. So why is it rotating? With a magnet on the axis, torque is zero, but if we move the magnet and hit the parts of our nickel of axis, such a device will start rotating, and we check this in the experiment. However, problems with such as an engine are also obvious. After all, the hit spots will be blurred over the surface, which will result in maximum speed, as well as bearing friction and electromagnetic braking. To study a Curie engine, we have constructed an experimental setup in which they could control heating, magnet fields, and geometric parameters. So we set the problem. To describe the motion of the disk, we need to know which area will be above the Curie point. And so let's start with dynamic heating of the disk. To solve this problem, we use the COMSOL numerical modeling environment. Using Fourier's law and equation of heat conduction, we taking into account the translational motion, we were able to calculate the establishment thermal picture. But we have one problem. In COMSOL, the heat capacity of nickel at the Curie temperature is taken as a constant. But in real life, our colleagues have built a model to describe the transition at the Curie point, where they took into account the inconstancy of heat capacity versus temperature, and we will use the result in our model. Well, results are worth it. After all, we can describe the size of the region about the Curie point depending on the temperature and so on the time. And now let's consider braking forces in the system. The force of electromagnetic braking must obviously be taken into account, but we can do this at the stage of calculating magnetic interactions, because it is magnetic force. As for the friction in the bearing, we will find his impact empirically. It should be noted that it greatly increases when the bearing is exposed to a magnetic field of the magnet. And well, the most interesting thing is consider the magnetic interaction in our system, and this is the general part of my report. We wrote a program that can calculate magnetic fields near magnets. In order to predict the field pattern, we only need the initial magnet induction that we measured. And we break the magnet into many parts according to the technique from the article from the previous slide, I'm sorry. And we take into account the impact of each of the parts of the magnet, and with a Hall sensor we measured the induction profile of our magnet and checked our model. Nickel has a domain structure, and it is magnetization depends on the induction of the external field, and it is important to take this into account in our study, in our investigation. For this, we worked exclusively in fields of saturated magnetization with strong magnets, and we checked some articles about this. Thus, we can consider the magnetic moment as a constant because we work only in saturated area. And this means that the force will appear due to the change in the magnetic field along the coordinate. And so we can express an effective torque. And after this, we express the corresponding vectors. We can also find the force acting on the disk, where the corresponding coefficients are obtained from our magnetic field model, and the volume of the non-magnetic part from the thermal model before. Our theory describes the experiment well, and indeed it reaches a constant speed under the influence of resistance forces, of blurring of the heat by the surface. And let's look at this problem parametrics because it is very important for the engine. There is also an optimization. There is, I'm sorry. The size of the disk affects both the moment of inertia and the heating area, which gives us an optimization in angular velocity. Also, we have optimization for the distance because we have two effects: increasing of friction brewing by the magnetic field, and also effective rotational force depends on the magnetic field. In addition, an important result is here calculation of efficiency of our engine. The maximum that we could get in %10s in experiment, but in theory, in the article, we can achieve a result of 27%. That much greater, but we have only nickel. We haven't nitrogen now, liquid nitrogen for the setup. We cannot start it. And so we measured the Curie temperature, considered the thermal evolution of the process, took into account the friction in the bearings, built the magnetic field, calculated the rotation, and tried to optimize our engine. Bibliography. Thank you for your attention, and I'm happy to answer on your questions.